Hey, MoNaCo here.
And Mr. Mills.
We're talking about atomic theory still. We're in Unit 2. What we're doing today is we're working with some pages in our pack, 16 and 17, talking about isotopes, what they are and how to figure out how much the average atomic mass of an element is based upon the isotopes that exist. So the first thing we got to know is the definition of isotope.
Definition of an isotope is an atom with the same number of protons but different number of neutrons, hence giving it a different mass.
Because remember, protons and neutrons are the only parts that have mass.
And they are in the
nucleus.
And this picture shows us real quick. I have three versions of helium. We're not going to test you on the names. You're right.
I am right.
I'm highly caffeinated. Notice I have one proton in each.
Pink, purple, yeah.
But the first one has no neutrons, the second one has one, and the third one has two.
So a total of three. So
total
you see
three, yep.
1 mass, 2 mass, 3 mass in the top left corner. That's how we get our atomic masses. Anyways, let's move on here with some additional notes on the isotopes. Isotopes are natural. Not all atoms of the same element are identical. John Dalton was wrong. Isotopes occur naturally on our planet.
And some of them have multiple isotopes, like in this case of hydrogen we just went through.
3 naturally occurring isotopes of hydrogen.
Yep.
Only the number of neutrons change from one isotope to another. It's like a pair of identical twins where one of them weighs a few pounds more than the other.
Sure. Or they didn't dress like a twin that day.
Right. For example, yeah, right. So it's still hydrogen, but this version of hydrogen has a bigger mass because it has more neutrons,
right,
or less.
Right. Isotopes definitely vary in their stability and function. So like this H3, for example, the tritium doesn't stick around very long. It deteriorates very rapidly because it is not stable at all.
And its function, they're trying to use it in fusion reactors here on the planet in research labs to make energy.
Right.
But hydrogen, one hydrogen, can't do that. So it has a different purpose than one hydrogen.
Sure.
Natural abundance is a fancy way of saying how many of each isotope occur naturally in a percent form. Like if you were to go take a cross section of the planet, how much of each isotope would you find naturally?
Right.
Not in a research lab, not in a nuclear reactor, out in nature.
Right. I mean, it goes to reason that hydrogen 1, hydrogen 2, hydrogen 3, there's probably a whole lot more of one of them.
Than the other two. Absolutely sure.
Right.
And that's where the weighted average calculation comes into play.
Right, so this is an average where a weight is assigned to each number instead of just adding them all up and dividing by however many there are. Like example, your test grades. Your test grades in your classes carry more weight on your grade than your homework grade does, for instance.
Right.
So we're going to use that and that idea to come up with this total average mass for a particular element. It should be a lot closer to the one that there's a lot more of.
Right. Okay, so let's check it out. So there are 3 steps in a weighted average calculation, and we have to use the natural abundance. So the first part is to determine the mass of each isotope. This is going to be given to you in the problems or in a chart form, and we look for the atomic mass. So for example here, for the first isotope, we got ourselves carbon-12. The first isotope is the 12. 12 point quadruple, quintuple 0 is the mass of each isotope.
The other isotope is the carbon-13. So its mass is slightly different. It's 13,00335.
Okay, so that's where we're getting the mass of each isotope from. Next, we have to multiply each mass by the percent abundance in the decimal form. Remember, 98% is the same as 0.98. Mathematically, a percentage is a decimal. So we take the 98.89% of carbon that is carbon-12, convert that into its decimal form, move the decimal 2 spots to the left.
Or divide by 10, however.
Divide by 100.
That's what I meant.
Don't divide by 10, divide by 100.
You got it.
Okay. But either way, to convert the percentage into the decimal form for both isotopes, we'll multiply obviously at the end here, but so for the second isotope,
we take that same number, or 1.11, divide it by 100, in the decimal form, multiply that out.
By the original mass, and we get this. So what these numbers mean is what the mass fraction is.
Yeah, this is how we weight it, actually.
Yeah, this is how we weight it. Because the last part is we take these two numbers and we actually add them together. So to add the weighted mass to get the total overall weighted average. And in this case, we see that the overall weighted average for carbon 12 and 13 is 12.011. And if I look at my periodic table, I see that it is, in fact, the average atomic mass reported in our reference
And
list.
this number also makes sense because 98%, almost 99% of carbon is carbon 12. So the average mass should be much closer to 12 than 13.
Yeah, a very, very small percent is heavier, which pulled the average mass up just a little bit. Now, we didn't count carbon 14 because it's radioactive and cosmogenic, means it's being created in our atmosphere as we speak. It doesn't stick around in the same way that carbon 12 and 13 do. So we don't include it in this particular calculation. So for any element, we have to do the same thing. Now, for this example, I'm going to set it up the same way. It's carbon 12 and carbon 13 in the same percentages that you just saw, but we're going to do the average atomic mass of the element in more of like kind of like a math multiplication kind of form that you might be familiar with. Mr. Milks, do we ever have to deal with more than two isotopes of one element?
Very rarely. Sometimes there's 3, but never more than 3.
Never more than
And a lot of times we get lucky where it just says, show me the correct numerical setup. It doesn't even ask for the answer.
math, right.
So learning the setup is actually what's
Right.
key here.
So numerical setup is the important part. We're going to walk you through that right now. I'll do the first term for my carbon 12, 98.89%. It says to take the percent abundance of isotope in decimal form, right there. Must have a bubble in the board there. So I'm going to take this percent abundance of my carbon 12 in decimal form. I'm going to open a parentheses, and I'm going to say 0.9889. And I'm going to close my parentheses and open a multiplication and multiply by the mass of isotope 1. Mass of isotope 1 is 12. Cool. So there's my first term. Mr. Milks will set up the second term in a different color.
All right, so I have my percentage that needs to go into decimal form, 0.01111. I'm going to multiply that by my mass, 13.
Okay. And so when we do the mathematics here,
Blue here.
equals answer 1 and answer 2, mathematically, you're going to get the same results that we did on the previous slide. So we're just cranking it out real quick on a calculator. See, the first term is 11.8668. 11.8668. Second term is going to be 0.1443. Now we line up the decimals, of course, and add those two together to get the products from step 1. There's two ways to do it. I'm going to do it down here. 11.8668 plus 0.1443 equals, what do we get, Mr. Milks? 12.0111, and we want to put the units A and E's on there, atomic mass units. And this is your overall average atomic mass for these two particular isotopes of carbon.
So isotopes are simply the same atoms with different masses, of course, because they have a different number of neutrons. The relative abundance for each element we calculate using the average atomic masses. And now we can do it. We just need lots of practice, so we can do this over and over and over again.
And remember, you don't practice until you get it right.
No, we practice until we can't get it wrong.
Right, absolutely. Search online for average atomic mass, weighted average calculations. There's a million examples that are not related to chemistry that might just click in your mind. Find it until you own it. Thank you all for watching.
See you tomorrow.